session because otherwise we'll be late for lunch. And that's always sacred, so we should not sacrifice that part. And okay, I don't really have to introduce Victoria. She is not the first-time speaker in this conference, so I guess all of you, or most of you know her anyway. But I think that the topic that she will be talking about today, knowledge representation, and you know it's a very important one because if you think about what session should be given this talk in, and if you look at the conference, can be in distributed intelligence, it can be in modeling, can be in data, can be in sustainability. So, and I think probably this is, we may see as, I wouldn't say most important talk, but definitely most representative talk of this conference. So Victoria, the stage is yours.
Thank you. Thanks a lot. So I will split my talk into 3 parts. In the first part, I will give a sort of a tutorial overview of the different types of representation models that you can find in digital twin systems, since we're a summer school, so tutorial is good to have. And then in the second and third part of this talk, I will show you some examples of what you can do by combining different representation models together to achieve better results in modeling the real-time digital twin systems. And I want to motivate my talk by showing this reference architecture. I saw reference architecture of digital twins, in this case for manufacturing. And I could have chosen any other reference architecture picture, because if you look at reference architectures of cyber-physical systems, digital twin, and other types of such systems, what you can see is that there's always some layers that you can find in all types of architectures. You start with a physical layer where your sensors reside, where your actuation resides. Then you have a communication layer that performs data collection, data preprocessing, controls the physical world, so performs actuation. And then you have the representation layer. I really like that in this reference architecture they call it the core entity, so they emphasize how important this layer is. This is where all the intelligence resides, all the modeling, the simulation, the interoperability support, and then you have the application layer. Here they call it a user entity, but I think application is a bit more emphasizing the fact that user is not only a human user, but also can be, of course, other systems that require some information from our digital twins, and the organization layer controls the whole system. So if we look at these layers, today I want to talk about the representation layer and consider questions such as how can we best represent the environment, the physical environment digitally? How do we know that we get sufficient information from the physical environment to represent everything that we want? What's the right knowledge abstraction level? How do we deal with evolution or drift of the systems? And how can we trust our representations? When we answer those questions, first of all, we need to consider the physical layer. We need to consider what kind of data we get from our sensor. Is this data sufficient? Are the sensors in the right locations? Are the sensors of the right type? Do we get everything we want, or there's some data missing? We also need to consider, of course, the applications, because we never model, we never represent 100% of our universe. We always model certain abstraction, we always model concepts, and there should be a reason for us to model those concepts, and the reason is the application. So someone needs to use the concepts that we model, otherwise we can abstract them away. And then of course we need to model the whole, we need to consider the whole system and consider non-functional requirements such as performance, storage, computational resources, maintainability of the system, and so on. So if we consider the representation models, there are 4 types of models that we can very often see in digital twin systems. And here is the overview of the 4 types, and now I will talk a bit more about every type. So the first is the mechanistic models. These are the models that are grounded in natural laws, for example, of physics, of chemistry, or biology. Usually we have a solid theory of how the world works, and we put it into, let's say, a set of mathematical equations. For most of the mechanistic models, we have very mature software that is domain-specific and represents the system very well, so you can simulate whatever you want. And the good thing about those simulation software is that when you have a solid theory and when when all system inputs can be reliably captured, and also all inputs during the time period that you want to simulate, then those simulations are very, very accurate and very precise, so you can really trust them. The problem with those models is that very often they are quite complex and computationally expensive to model. And also, they require a lot of information about the physical state, the initial physical state, and the progress of a physical state, so all the external inputs. So they need to be calibrated in order to model what we want to model. The second type of models is data-driven models, which is different types of machine learning. We use them when we not fully understand the underlying physics, or we want to abstract the physics away. Obviously, while training can be computationally expensive, using them at inference time is very fast and very cheap. And also they do not require full knowledge of the system, so you can only provide them partial information about the environment if this is sufficient to model the whole environment. But then you need to have historical training data or synthetic training data, so you need to have a lot of training data. The next type of models is the logic-based formal models. Again, it's a mathematical, mathematically justified representation. For example, based on formal logic, based on state-based representation, process-based representation. They allow you to do verification, they allow you to do model checking, and even they prove correctness. And the final type of models are ontology-based models. Usually this is like interoperable structured vocabularies of concepts and relationships. The interoperability here is very important because this is the design idea of ontologies. So you, for example, in a case where you need to compose complex digital twins from a system of more smaller digital twins, you can do this through ontologies pretty easily. And this is a representation that is machine processable, but also human understandable conceptualization of a certain domain. Okay, so I showed you these representation models, but the most interesting stuff we can do when we combine the representation together. And I want to show you some ways to combine those representations, ways that are currently being researched in the different directions of research. It's not all of them, but at least those that are on the picture I want to briefly mention. And I want to start by considering the mechanistic models and the problem of calibration. So I already mentioned that for mechanistic models you need to know the initial state of the system. In most cases, what you have in digital twin system, you can use mechanistic models to try to simulate, to model the current state of the environment. But what you have from the current state of the environment is sensor measurements. And going from sensor measurements directly to the model parameters are not always a straightforward task. Sometimes it can be quite a complex task. So we have systems that are called auto-calibration systems, which is systems that do calibration automatically, but normally the way they operate is through the optimization loop. So you consider some models, or you consider some parameters, you run the simulation, you see whether it corresponds to the measurements or not, and then you, in optimization loop, you converge to the measurements that you see. Now, the problem is, of course, that if the mechanistic model itself is already pretty complex and computationally expensive, then running this in a simulation loop is even more complex and even more expensive. So there's definitely the real-time connection in the digital twin case breaks in this case. So it takes quite some time to recalibrate the system. What we can do to avoid this calibration is to perform surrogate modeling. Surrogate models are usually data-driven, simplified models of the mechanistic models that basically mimic the behavior of a mechanistic model, but in a more straightforward manner. And they can be very fast at inference time, so we can immediately know what's going on in the rest of the system that is not directly measurable by sensors. So they can work on the partial observability. And very good for the surrogate model is that they can use the original mechanistic model as a source of the training data. Of course, then they do not explicitly model the underlying physics, so their problem is that they lose the interpretability of original models. And in some cases, if there's some rare anomalous behavior, they can also miss some rare or specific behaviors. Another way to combine the two models is through inverse surrogate modeling. Here the problem is in reverse. So you have the measurements, and what you want to know directly is the model parameters of a mechanistic model. This is exactly what auto-calibration is doing, but if auto-calibration requires you to run mechanistic models in a loop, inverse surrogate modeling avoids this, right? So it removes the mechanistic model from a consideration, and it has been trained directly to infer the model parameters from the sensor measurements. Very commonly, the problem for such inverse surrogate models is the one-to-many mapping, so you can have the same sensor measurements for different initial states. So in this case, you either need to get extra data, or if this is a system that you can control, you can add optimization, for example, decide on the most energy efficient state and so on. Another type of connection that you can do between mechanistic and data-driven is the physics-informed neural networks, and I'll talk about it in an example. But this is where you can considerably improve the performance of your data-driven models if you consider the domain knowledge, if you consider the physics during the training of those models. For example, in the loss function, in the way the model is trained, and so on. Now, mechanistic models and logic-based models are both formal models, and data-driven and ontological in principle are less formal. So some representation models are both logic-based formals and mechanistic when they describe the environment, although usually the way we use those words is we apply mechanistic more to continuous systems and formal models more to discrete systems. But very often you can find also hybrid systems. For example, a sort of a final state machine where you have like a thermostat being on or off, and you have a set of mechanistic equations that are different in each state. So it allows you to keep the complexity down while still having a powerful mechanistic model inside it. But what we also see in like the common difference in the way we use those models, that mechanistic models usually describe the world, while formal models represent the requirements, right? So if a mechanistic model, if a model disagrees with the measurements, if it's a mechanistic model, then the model is wrong, we need to update the model. But if the logic-based formal models are wrong, then it's not, the model may be right, and the reality is of course the reality, so it cannot be wrong, but it means that the real system does not conform to what we wanted to do, so we need to change something. There's a number of ways to perform the formalization of the system. From data-driven to mechanistic, you can perform symbolic regression, so you can extract the equations from the raw data, both the form and the parameters of those equations. From data-driven to logic-based formal, you can perform things like rule learning, process mining, and then from ontological to rule-based to logic-based, you can perform schema validation or data validation according to schema, like shackle rules and so on. And one more last thing I want to say about that is that there is a lot of work being done in the unification across domains of the models. One of the things are the foundation models, so there can be domain-specific foundation models that are trained on the data sets of a specific domain, but there can also be domain-independent foundation models that are trained on, let's say, data sets from different domains, trained to solve a specific task. And another way to perform domain unification is by including ontologies. So you abstract away, let's say in the physics-informed neural network, the physics goes directly into neural networks, so it becomes domain specific. But you can abstract it away into ontology, and it's a much easier way to change the physics if you want to apply your pipeline into a different domain. So you can perform domain specification in tautology and then apply it to data-driven system. And I'll show you how it works on the first grounding example, which is the hydrogen. So this is a state estimation of water systems problem. And in our case, so you already know the problem because Esther told all about it. We had a lot of challenges such as a very extreme sensor sparsity, only 1 to 5% of the network. And mechanistic models require a lot of expensive calibration, so you have trouble using them in real time. And then also we applied it both to drinking water network and to wastewater network. And then in wastewater system, there's also a very considerable uncertainty levels. So there's a lot of external influence to the system that you need to deal with. Yeah, that's our project. To solve this problem, we created a huge data set that Esther already talked about. So this data set contained a lot of different network topologies, a lot of different parameters, dynamic parameters, static parameters. We ran a lot of simulations through the mechanistic models to create a lot of different scenarios. And this data set is now published and available for any type of water research. And we had the mechanistic plus data-driven pipeline. Basically, we used our data set to train a graph neural network for state estimation. So we would mask most of the network, only keeping locations where we assume the sensors are, and try to reconstruct the rest of the network. And it worked very well, so we were much better than the other state-of-the-art models, and very importantly, we were very, very close with what a mechanistic model tells you, even though our surrogate model that we trained worked much faster and required much less information about the environment than the mechanistic model would require. Okay, so that was the work on the drinking water network. But then we decided to apply the same pipeline in a different domain, which is a wastewater. And the pipeline itself, if you look at it, so that part should be domain independent. The only thing that you change is the actual simulation, so the mechanistic model, and well, the proportion of the data set is actually the same. So also here you don't need to change a lot. So we applied it to a wastewater system in Heusden in the Netherlands, which is near Den Bosch city, if you know it. And originally we got results with the original our gut-rest model, which is the architecture that we trained. The results were okay, so they were better than the previous state-of-the-art model. So we already were happy to publish those results. But they were lower than we would want, let's say it like this. So the difference with the mechanistic model was greater than in a drinking water scenario, but also to achieve levels where, let's say, water engineers would be satisfied with our model, we would need to increase sensor coverage. And water engineer told us that, okay, that's not possible. You need to keep below 5%, otherwise we cannot use it because it's not achievable in practice. So we started thinking of what can be improved, and what can be improved is by introducing the physics into the neural network. So in the case of a drinking water network, we treated the whole graph homogeneously. There are some variations between the nodes in the network, but you can treat the graph homogeneously and still get very good results as we got it there. But in case of wastewater, the locations are very, very different with very different underlying physics. So you can have like a manholes, like normal junctions, outfalls where the water can go out of the system, storage, and then as connections you can have conduits, so like the connections, then pumps that increase the water flow, and weirs where there's like a wall and the water needs to go up, the level needs to rise before it flows further. So we decided to have in our neural network different types of nodes according to this physics, and see whether we can train the model if we consider this heterogeneity of the network. So our graph at the end looked like this. We also, what we've done, we also added edges, so the connections of the physical graph, as a separate nodes to our graph that we modeled in the neural network. If you see this graph, what does it remind you? It's an ontology graph. So it's a graph where each node has its own type, and the type has a number of parameters, features. So if you define the same schema, you can define the data that is specific to a certain domain. And then what happens here is that if you do it in this way, the whole pipeline of training the neural network stays domain independent, because all important physics-informed domain dependency is abstracted away from it. Another way that we've done is by introducing message passing from further away nodes, so not only from direct neighbors. And finally, what we also done is introducing the loss function that incorporates a non-physics constraint. In case like a flow conservation, so that the water does not appear or disappear, a Mannion constraint, which tells about the maximum flow of water, depth monotonicity, and water level monotonicity. And in our case, by doing that, we were able to achieve about a 79% reduction compared to state-of-the-art models, and the average error of water level was about 12 centimeters. And to give you a perspective, water engineers are happier when they have the average error below 30 centimeters. So we made our collaborators very happy with these results. But what's really important and what's really interesting is to look at the graph here. So the original gutters architecture, the one that we used for drinking water network and we applied without any changes to the wastewater network, already had about 50% improvement over other state-of-the-art model. But when we added these physics-informed constraints, we achieved another 50% improvement over state-of-the-art network. So, and this was under 5% sensor coverage as well. But what's also interesting is if you look at this graph that shows error depending on the distance of the node from the nearest sensor. So the distance starts from 1, otherwise like 0 is the sensor itself, then we assume of course that we know the values. With previous state-of-the-art models, you see that already very close to the sensor, the error is relatively high, and it grows a little bit with the distance. With our gutress model, initial model, the error very close to the sensor was very low. That was the reason why we achieved this considerable improvement. But as you moved away from the sensor, the error grew very rapidly. As soon as we added those physics-informed constraints, we could keep the error very low. Also, when the locations were distant from the nearest sensor, by basically propagating the physics. So that is also the results that obviously makes the water engineers very happy, because then they can know, okay, we can have sensors just in few locations and then still trust our results. Another grounding example I want to talk about is the extraction of rules from raw data, so neurosymbolic rule learning. This task is about if you have raw sensor data, you want to find patterns in the data, you want to describe certain behaviors, certain conditions, and you can find patterns in that form. For example, if variable 1 equals to a certain value and variable 2 equals to a certain value, then we know that variable 3 also equals to something else. And this is called associative rule mining, so it's a known problem. The problem with classical methods is that they are absolutely not scalable, but also that they produce rule explosions. So they produce a lot of rules. Rules are a little bit different from each other, so they kind of describe the same situation, but with a little bit of variability. And choosing the rules that you want to use is yet completely another problem from just finding the rules. So that makes like using rules for downstream tasks much more challenging. So yeah, this is just the example of a task. If you have a table and you have a lot of features, then you want to extract rules that, for example, either for a certain class or in an unsupervised manner for any feature in the consequent. So a couple of years ago, we introduced neurosymbolic architecture for learning those rules by using the autoencoder. To briefly explain you how it works, if you have your tabular data, you can train an autoencoder to extract this data. And of course, what you have in the middle part of an autoencoder is you have the compressed information that must already have patterns in it. So your task is to extract those patterns into interpretable rule form. So this is what we've done. Basically, once you trained autoencoder on the tabular data, we use this autoencoder to extract rules for the situations that we care about. So we could say, okay, if we know certain values of certain sensors, what else can we say about the situation? And then we would create a vector where we would assign values to sensors that we know about, and to the rest of the features we would assign unknown values. And then we reconstruct the encoder, and if certain values are closer to 1, so the high certainty, then we know, okay, we can extract a rule that implies that this will be the value of a certain other value. Okay, so that neurosymbolic architecture already showed a huge improvement over the previous methods. And what's very important is that it's very scalable. So if you look here, the aerial is the blue, and it's a logarithmic scale, so it's 10 to 1,000 times faster than alternatives that we tried. Okay, but that was, as I said, work from a couple of years ago. But this year we were also, forgot to say, we have a library that is published. It's very well documented and it's very easy to use, just a couple of lines of code. So if you ever want to perform rule learning, you can very easily use this library to perform rule learning. Okay, so this year we were busy with questions of how can we extract those patterns from cases with low data. What it means is that if you look at this, if a lot of medical data sets have this problem, you have a very small number of rows, but you have a lot of columns. For example, here, each person has thousands of genes. And if you perform a certain medical procedure on a person, you can get a test and show the expression level of every gene. But performing the medical procedure is complex, so you only have a few samples. So the number of rows is limited, but the number of columns is huge. And classical methods die in this problem because they're designed for the opposite problem, where you have a lot of rows, but just a little bit of columns. There's also optimization-based methods, like nature-inspired optimization-based methods. They also fail because in many cases they cannot find all the rules, so the coverage of the data set is very low. So we wanted to know how our aerial architecture works. But also at the same time, while running the experiments in our aerial architecture, we also got acquainted with tabular foundation models. Just to give you a brief overview of what this is, the tabular foundation models is it's like a large language models, but large tabular models. So they're trained on millions of tables. Tables, in the case of TabPFN, which we used, tables are synthetic. They're created with different causal relationships. And each data point for training is the whole table, where you provided the training data, and then the test data with unknown labels. And then the goal is, of course, to get the labels and minimize the error. And then in the inference time, you give to a tabular foundation model, again, the whole table with the training data and the test data that you want to get the answer for, and it immediately gives you the answer. And what was shown is that those tabular foundation models are very good at especially low data regimes, because they use this prior fitted knowledge to extract the patterns even in cases when the data in the table itself is limited. So what we've done is we tested aerial itself, just the aerial without any additions on data sets with low data, right, with a low number of tables but huge number of columns. And then we also applied tabular foundation models in two different ways. In the first way, we use tabular foundation models as for weight initialization. So the way it works is that you have your data set, you run through tabular foundation model to get the table embeddings, and then you train very simple projection encoder, in our case it was like two layers, to encode each data point into embedding that the tabular foundation model gives you. Okay? So once you reach levels with this projection encoder, what you do is you take the first layer of this projection encoder and insert it directly into IRL autoencoder as the first layer. So you perform this weight initialization. That already made it even better, but I'll show you the results later. Before I will show you the second way that we tried, which is using the double loss. The first step was exactly the same as here. So we have the table. We run it through the tabular foundation model to get the table embedded, and we train the projection encoder in a very similar way, but now after the reconstruction instead of before the reconstruction. So we don't train it on the original data, but we train it on the reconstructed data. So we run the pre-training part where we try to reconstruct the table from the autoencoder and then put it through the projection so that the reconstructed vector corresponds to the table embedding of the tabular foundation model. And then at some point when we're happy with the results, we stop training the encoder, so we fix it. And then we start the actual training stage. So now we train the autoencoder, but using the two loss functions. The reconstruction loss function, which is the normal one, plus the loss of the difference with the projection that the projection encoder gives us. And what we can see is that actually by adding the tabular foundation model, we could achieve, we could learn even less rules, so be much more precise, while keeping the confidence higher in all cases, and also the chance metric, which is the kind of the how much more likely the rule is to happen, not by chance, but by the actual correlation, is also much higher with aiding the information from the tabular foundation model. We didn't stop there, because what we also saw is that we still use our IRL architecture in the training, so we still need to train it through the autoencoder. But actually, can we use the tabular foundation model directly to learn the rules without any training through the autoencoder? And the way we approached this problem is by the tabular foundation model itself, they're designed for the classification task, right? So they're designed to reconstruct the label. So the way they're implemented right now, they're not designed to learn rules. But there is a way to transform them so that they are capable of learning rules. So what we've done is basically we have a table that we want to use for learning rules. We give it to a tabular foundation model, and we define which features we want to we have information about, so which features are sensors, and which features we want to learn. And then this is given as a constant, the tabular foundation model. And then we have a prop matrix, which is our test part of the data set, where we define the parts of the features, like we define different situations, and what we don't know, we just give the equal probability, and we ask tabular foundation model to reconstruct those features that we don't know. And then it gives us the vector in exactly the same way as IRL autoencoder would give us, so that if certain reconstructed values are above the threshold, that we know, okay, we can learn these rules. And what's very important is that if you compare the results, if you look at the large tabular data sets, so data sets with lots of information, you can see that there is like this Pareto optimality between IRL and tabular TAP-PFN, where IRL produces a bit less rules, which is good, but also with a bit less quality. But the tabular foundation model produces a bit more, but with a bit higher quality. But if you look at the small tabular data sets with small data, here the tabular foundation model is basically better than everything else. So it actually can extract a lot of information already from even small data sets. So that's it. Thanks a lot, and yeah, ready for questions.
Yeah, thank you really a lot for the talk. I greatly enjoyed it. I'm not sure if you remember, but we also work a lot in discovering this sort of mechanistic or symbolic rules that, let's say, govern processing systems. And I found it very, very nice, the relations of transitions that you showed and how to improve a model. But I was very often asking myself, like, because you do all of this in an offline manner, basically, or have you ever tried to employ this is sort of, let's say, evolving architectures that would, let's say, collect data? Because I mean, all of these methods that you showed, they're not continuous mechanisms in the sense of. And have you? So could you tell a bit more? Do you think it would be realistic to employ this in also, let's say, runtime architecture? Because I think in your examples there is also no distribution shifts usually, so there is no need to refit mostly.
That's not part of my talk, indeed. So my talk does not consider distribution shift. However, we do have work in this direction with test time training, which Esther also briefly mentioned. The way you do it with test time training is basically, so you train your model to, for example, for state estimation. And then once the model is trained, what you do is when you have new data points, you have you test new data points on two things. So first of all, you have the actual task, for example, the reconstruction. So you don't know the ground truth there, right? So you don't know how good your model is with the new data that you receive. But you also have the self-supervised task, which you can know the ground rules, for example, like the shortest path or something like that. Very simple. And when you have new data points, you test the data points on the self-supervised task, and then you see whether the supervised task returns you the same accuracy as before or not, or whether the accuracy drops. And there is a way, there should be a different talk on that, so I'll not go into this, but there is a way to, during the training, like the matrix that you learn in the self-supervised task, you apply it also to the real task, so that in order to improve accuracy of the self-supervised task, the change that improves the self-supervised task also improves the accuracy of the real task where you don't know the ground truth.
Okay, thank you. Happy to learn more.
Actually, I'll show you the preprint. We just published it like a week ago. Yeah.
Thank you very much for giving us an overview of your work. You call your tabular foundation model a foundation model. Why do you use the term foundation model for the work?
Just to be clear, tabular foundation model is not our invention. There's a lot of people working on that, and there's this. So the paper that I mentioned as one very influential paper on tabular foundation model. It's a foundation model because it gives you the answer on the whole data set directly. You don't need to train a model per data set, right? So you don't take one data set and train it on the train part and then test it on the test part, but you give it basically, you give the new table once, the model does one forward pass in exactly the same way as you give a prompt to a large language model and it gives you the answer. You give a prompt, which is a table, and it gives you the answer.
Thank you.
Okay, then I guess but I'm actually very interested in one specific part, because you in the beginning mentioned that mechanical modeling is very, very hard in a way. It's calibrated, it's very complex mathematically, and overall takes a lot of efforts. But at the same time, you're presenting this combination of mechanical and data, and you say that you enrich with physical, properties of things. How complex is that? Because if you bring this mechanical world into the data, so how complex are those rules? Let's say, more general question, how transferable is this approach to other domains? Do we need, let's say, water experts I don't know, experts in manufacturing and so on, because those probably very specific, domain specific and very, very complex.
Yeah. So regarding how transferable is this approach, there is, I can give you an example. We have a lot of AI engineers, right? So AI engineer can come to a certain, let's say, domain expert and say, I'm an expert in AI, I will make you a model that will predict your data. We don't have experts in mechanistic models, like general experts, right? Expert in mechanistic model is an expert in a domain. It's like hydrologist for hydrological models, physicist for, let's say, nuclear physics. You cannot say, I know nothing about nuclear physics, but I'm an expert in the mechanistic model, and I will create you a great mechanistic model for your nuclear reaction. But you can say, I'm an AI expert, and I will create you a great AI model for a nuclear reaction. So that's why like moving to the data-driven by default allows you to perform much more, I guess.
Yeah, thank you. Unless we have more questions, I guess we can safely, say thank you again to the speaker.
Thank you.
And I guess we will see each other in the afternoon session. Thanks.
Ich will die nächste Session sparen. Was anderes machen. Aber das ist der größte Session. Wo ist die denn? Von der Rezeption kommt Wenn ihr von der Rezeption kommt, ist das so eine Soundstufe, die automatisch das Gegenüber der Bar. So habt ihr das. Ich muss schon mal anfangen mit Änderung. Das hast du wahrscheinlich mal
It's just because of the implementation of it. So we also try to do all of these things. It's train of regulations. But directly design so that you can have a lot of people at the same time. But it's again, it's basically just the classification is the task